Let's go over the Dalton's law of partial pressures and more fraction gases. Now, from the Dalton's law of partial pressures, well, for a mixture of gases, say you have got a container, you just don't have oxygen, but you've got also nitrogen, you've got fluorine, so different gases. To find the pressure that these different gases are going to be able to exert on the container is going to be a sum of their pressures. And so you say the total pressure, P total, is going to be pressure 1 plus pressure 2 plus pressure 3, and so on like that. So this is the Dalton's law of partial pressures. Now we also know that from the ideal gas law, pressure times volume is equal to nRT, meaning that pressure is going to be nRT divided by volume. So when I'm talking about pressure 1, it is going to be N1 multiplied by R multiplied by T1 divided by V1, and that will be plus N2 multiplied by R and then T2 over V2. We are going to have also N3 multiplied by R. For R, I'm not putting 1, 2, or 3 because it is a constant. It is the same for everything. So this is what we are going to be able to have. So if we are taking this to be at constant temperature, because we're only talking about the pressure of a gas inside an enclosure, or let's say inside a container, then the temperature is going to be constant. So also for the temperature, I'm going to remove the 1, the 2, and also the 3, since the temperature is going to be constant in the container. So from there I can get to remove what is common. Now before then, since the container's volume is also not changing, meaning that the volumes are also going to remain the same. The volume of the container is constant also. So I'm going to remove the 1, 2, and 3. So what might just be able to change is the number of moles of gas, because they're in the same volume, they also at the same temperature. So if I can factorize out RT over V because it's common, we are going to have N1 plus N2 plus N3, and then at the end, now this is supposed to be plus those dots because it continues to go like that, and then at the end factorize out RT over V. Now this N1 plus N2 plus N3 continuing to go like that is the total number of moles. So that will be total number of moles multiplied by RT over V. So this is what gives us the Dalton's law of partial pressures. So if you want to calculate the total pressure in a container, you just get to calculate the total number of moles and then multiply by the universal gas constant and then the temperature, then the volume, because it's only the number of moles which is going to be different. The rest are going to be the same. Let's also get to consider something called a mole fraction. Now the mole fraction is simply the number of moles of a given component in a mixture in comparison to the total mixture. Let's say you have got oxygen, but you also have nitrogen and other gases. Now let me just say the moles of oxygen in a container is, let's say, 2 moles. And then oxygen is in a total mixture which has got, let's say, 20 moles. So mole fraction given by the symbol X will just be the moles of one of the components, so the moles of oxygen divided by the total moles of the mixture, that is 20. And so the mole fraction is going to be 1 over 10. So from this same knowledge, now let me use an equation. We are saying mole fraction, I'm going to put a 1. So mole fraction is given by number of moles of a certain compound divided by the total number of moles. Now I've put 1 here because I'm talking about this gas only, the first gas. If you're talking about the second gas, I can put a 2 there. Now we also know that number of moles total is given by number of moles 1 plus the second number of moles plus n3, and then plus it continues to go like that. Now from here, number of moles 1 is going to be given by, we know from the universal gas law, we have got PV being equal to nRT. If I make number of moles subject the formula, that is going to be PV divided by RT. So we are going to substitute this on top there. So where there is N1, we are going to get to substitute this. So N1 is going to be equal to P1 multiplied by volume. Remember, volume is constant, right? Also, the R and the temperature, they are also constant because we're talking about the same container. So that will be P1 and then V over RT. This is going to be divided by, we go down, we have got N1, so that will also be P1 V over RT. We go to the next one, that is going to be P2 V over RT. And then the next one, that is going to be P3, going to have V over RT like that, and it continues. Now from what we have here, I can also, in the denominator, I can also get to factorize the V over RT since it's common. So we're going to have P1 multiplied by V over RT divided by, so we are going to factorize out, so we're going to have P1 plus P2 plus P3 plus the partial pressures will continue like that. Now the V over RT is common. So from here you can see that the V over RT will cancel with the V over RT because it is the same. So therefore the equation mole fraction is going to remain as P1 divided by P1 plus P2 plus P3 plus like that. So the mole fraction of this phase gas therefore is going to be pressure 1 divided by the total pressure. So apart from saying mole fraction is number of moles of a gas divided by the total number of moles, we can also say the pressure of a gas divided by the total pressure, or the partial pressure of a gas divided by the total. Let's consider this one. The partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure, that's atmospheric pressure of 743 torr. Calculate the mole fraction. I know that mole fraction is given by pressure 1 divided by the total pressure. So we've been given the pressure of oxygen, which was observed as 156 torr, divided by the total atmospheric pressure, which is 743 torr. You need to make sure that the unit of pressure is the same because mole fraction is a ratio, so don't expect it to have a unit. The units are supposed to cancel out. So this is going to give us about 0.210. That is going to be the mole fraction. The next one, the mole fraction of nitrogen in air is 0.7808. Calculate the partial pressure of nitrogen in air when the atmospheric pressure is 760 torr. Again, you know that mole fraction is given by partial pressure of a gas divided by the total atmospheric pressure. The partial pressure is 0.7808. That is going to be equal to the partial pressure of a gas divided by the atmospheric pressure, that is 760 torr. So when we want to remain with P1, we simply multiply the 0.7808 by the 766, and that is going to give us 593 torr. So that is going to be the partial pressure of the nitrogen gas. Let's just consider this last question here. Calculate the mean square velocity for the atoms in a sample of helium. When you're talking about mean square velocity, simply the velocity of a gas. Now it is a special kind of velocity, and so the mean square velocity given as u with this is given by the square root of RT divided by the molar mass. That's the formula for mean square velocity. So this is going to be square root the universal gas constant that we are going to use on this equation is 8.3145. So you don't use the 0.08206 here. Now we are using this one because this value of the universal gas constant has to do with energy. It has to do with a joule, and we know a joule is equal to kg meter squared per second squared. So we are going to multiply this by the temperature. This is at 25 degrees. Now we need to convert that to Kelvin, so that is going to be 298 Kelvin, and that is going to be divided by the molar mass. Now I've been taught to calculate the mean square velocity for the atoms in a sample of helium gas. So if we get to check helium gas itself on the periodic table, the molar mass, the molar mass is about 4 for helium. So that is 4 grams per mole. Now when we are using this molar mass in this equation, because we can see that the value for the universal gas constant that we are using is in kg meter squared per second squared, we need to make sure that we convert this value to kg. So to do that, we have got 4 gram per mole. We are going to multiply, we're going to take a gram down and then a kg on top. We know that in 1 kg I've got 1,000 grams, so the gram cancels with the gram. So therefore that is going to give us 4 multiplied by 10 to the power negative 3 kg per mole. So that's the value for the molar mass that we're going to use in kg per mole. It is 4 times 10 to the power negative 3. Therefore the value that we're going to get in this case is going to be 1.36 times 10 to the power 3 meters per second. That is going to be the mean square velocity of this sample of helium.